There it is, full screen. Okay, so now I'm presenting sort of an old idea that I also presented last time, actually, at the last meeting 1 year ago. And I also used some of the slides that I used last time. So if things look, if a few of the things look familiar to you, that's because you paid attention last time. So now the idea here is to look into something we always talk about, numerical diffusion, numerical viscosity, especially in the pencil code. But nobody has really addressed it, at least quantitatively, especially in the pencil code. And so this is a project, a small project that I did with a student of mine, Ailey Ryan. She's a fourth year student. Actually, she just finished a project. And the idea here was to look into details on numerical diffusion, maybe also in the context of wave damping. And of course, the motivation came actually from back when I was doing my PhD, because everyone was talking about numerical diffusion, numerical viscosity, but nobody could really explain in detail what it is. And I've seen many people in solar physics and astrophysics using numerical codes and talking about it, but it's I always had the impression it's a bit like teenage sex. Everyone's talking about it, but nobody really knows what it is. So, and I think it goes back to when I was doing my PhD, when I was asking Axel and also Druba at the time. I think they also showed, they actually showed the idea behind numerical diffusion, that it comes from the discretization of your equations. And the idea is that by discretizing equations, where you're not, so you are not finding a solution of the MHD equations, but you're finding a solution, an exact solution of some modified equations. So MHD equations plus some error terms. And I'm not quite sure if you're still there because my Zoom sometimes cuts out. Are you still there? Can you still hear me? Hello?
Yes.
Yes.
Okay, good. Okay, because Zoom sometimes dies on me. Okay, good. So so in Glasgow, I've had the pleasure to teach numerical methods. Actually, the third time now, and students are actually having the exams next week on that. And there was a course by Radostin Simitev, who's done also a lot of work on dynamo theory using his own code, who's also in Glasgow. And now in this lecture notes, so this is actually a screenshot of the title of the lecture note. So in these lecture notes, of course, we talk about all kinds of things on numerical methods, linear algebra, linear systems, and of course also ODs and PDs, right? And as we saw by Naveen on Wednesday, we can discretize our equations by discretizing our derivatives, right? So when we have, say, where's my cursor? Second order spatial derivative of some quantity u, we can discretize it, something like this, have a second order stencil. This is a second order derivative, second order accurate. And by doing that, we can sort of discretize our equations, right? So our PD or OD, we can discretize it by using these methods. And now this is now our discretized problem, which I call A. H is the grid spacing, just a parameter. So A is the discretized problem, where L or curly L is the exact problem. So this one here. Now, if you go back to Naveen's excellent introduction on numerical discretization, you will see that this discretization is of second order, and you can do that, as Naveen also showed, by using the Taylor expansion of that. And if you do that, you see that your discretized problem has actually some different form. So it's essentially the exact form that you had before, right? Plus some error term. And what it actually means, which I always find fascinating, is that by using this numerical method, you're not solving this equation exactly on your finite number of grid points, but you're solving this equation exactly on your finite number of grid points, right? So you actually do find an exact solution using the numerical methods, but not of your original equation, but of the equation plus the error terms. And these error terms can be calculated explicitly by using Taylor expansion. And if you can go back, you can also ask Naveen, he knows everything about it. And that's the way you can do that. And actually, I was a bit surprised on Wednesday because we actually teach these methods exactly the same way as Naveen showed them to us on Wednesday. So using the tail expansion. So I was quite happy to see that. Now, the difference now between the numerical discretized problem, A, and the original problem here, we call the local truncation error. And if you do that, you can find, okay, the local truncation error for this problem using this numerical method is of second order. And again, using tail expansion, you can compute all the terms of this. And of course, that's very difficult to do analytically because you get pages and pages of calculations doing this, especially for MHD, using sixth order finite differences. I mean, it's already quite a bit involved using second order for this simple equation. And actually, that's something I'm doing with a different student, with another student. We're actually calculating these terms analytically. Okay. Now, how does this apply to MHD and the pencil code? So if you look at our MHD equation, so we get our unknowns on the left-hand side and our knowns on the right-hand side. And we have all kinds of spatial derivatives here, right? And then we discretize those derivatives. Now, by using our sixth order stencils, the default and pencil code, and also by using our Runge-Kutta method, we are not solving these equations exactly, but we're solving these equations plus an error term exactly. And of course, the basic idea behind numerical diffusion is that instead of actually finding an exact solution of this, you find of the original equation, you find an exact solution of this, which has a truncation error term. And now the idea is that some of this might have the form of a diffusion, with eta star being the numerical diffusion. So that's the idea behind numerical diffusion. Now, again, as I said, you can in principle calculate this tau exactly, using an infinite Taylor expansion. And then you see that is highly nonlinear. It depends on all kinds of quantities. It might depend on B, on J squared, on all kinds of derivatives of them. But here I want to show you more, instead of an analytical approach, a more experimental and numerical approach. Because in principle, we could measure this numerical diffusion by designing an appropriate numerical experiment. And one of them is Alfvén waves. So we look at linear Alfvén waves, with a strong homogeneous background magnetic field as a small perturbation perpendicular to the magnetic field. And this perturbation travels with the Alfvén speed along the magnetic field. And then, we have the usual equation for the linear wave. And here we have this omega over here. Now, if we linearize the MHD equations, we can look at Chandrasekhar's book from the 60s and see the derivation of the dispersion relation. We can see the linearized MHD equations, and we can see how we can derive an expression of omega. Now, of course, for undamped or undisturbed Alfvén waves, this omega is a real quantity. Okay, but so this is a real quantity if your viscosity is 0 and your magnetic resistivity is 0. It is a real quantity. Now, with viscosity and resistivity, this is not just a real quantity, it's a complex quantity with a non-zero imaginary part. And if this one is positive and imaginary, of course we will have a e to the minus something t. So that's our wave damping, which I now call lambda. So that's our wave damping parameter. And if you look in Chandrasekhar, although I think he was not the first one deriving that, there was some papers in the late 50s. And you can see that this lambda, this wave damping parameter, is actually just 1/2 times the viscosity plus resistivity times the length scale k squared, which is interesting because it depends equally on the viscosity as it depends on magnetic diffusion. Now this is explicit, right? Now the idea is, well, if you have some magnetic diffusion and magnetic resistivity, magnetic viscosity, then would also translate into some kind of numerical damping, numerical wave damping of Alfvén waves. That's why, we can think of a very simple experiment, numerical experiment. We have a strong background magnetic field, an Alfvén wave, it's traveling. And this is something we can easily measure by looking at the amplitude of this wave in time, right? So we can just measure the damping of our phase waves. And here I'm showing you a numerical experiment done with my student Elid. And here we're using the different viscosities and diffusions between 10 to the minus 1 and 10 to the minus 6, and also different resolutions. Actually, this is a lie. This actually goes from 8 to 256. I have some new simulations on that. Okay, so we use also different grid size, number of grid points. And ideally, we would like to see dependence on n, right? And maybe I can show you, because I'm sharing my entire screen, I can just show you real quick. How this looks like. Okay, so here, so this is just a plot of one of the simulations. So what you see in this plot is the wave amplitude in time. So horizontal is time, vertical is the wave amplitude. And that's a single logarithmic plot. So you see exactly an exponential decay. Okay, and then what we do is, okay, we have with these data points, we want to know the slope of this, because the slope of that is lambda. Right, so e to the minus lambda t. We do our least square fit, and we get lambda. And that's the total lambda, which is composed of the explicit lambda, the physical one, and the numerical one. So it's lambda plus lambda star. And of course, we know exactly lambda, so we can just take the difference to get lambda star. Okay, and that's what we do here. Oh, sorry. Okay, that's what we do here. So here I'm showing you a plot where we computed the numerical lambda, the numerical wave damping, which is supposedly composed of the numerical viscosity plus numerical diffusion. And I'm showing you this for different grid sizes. And here we have quite a bit of data. So the blue crosses. So for, say, a fixed number of grid points, the blue crosses are for different viscosities and resistivities, explicit ones. And you see there's not much of a difference here, right, in calculating the numerical diffusion. And this is for different grid size. We see also this power law, n to the minus 3, which is something I didn't really expect, because I expect a much steeper slope. Because using a high order spatial derivative, you would expect relatively steep slope in this one. And on top of that, Pat's code has adaptive time step. So you would also see an additional decrease of this by decreasing the time step. So it does not just depend on delta x, but also on delta t, right? So that's something I would expect. So that's the slope we find, minus 3 into the minus 3, which I think is relatively shallow. I'm not quite sure what to make of that. But again, so these are simulations that are, so the latest one I basically just finished on Wednesday, I think. So that's just something I need to look into in some details. But then, of course, we also did simulations with zero resistivity and viscosity. So those are the circles. So I actually set it exactly to 0, which I can show you in this one. So you see in this simulation, my eta is 0. And mu is also 0. And because it's just a simple affine wave, the simulation does not crash. So it's not like a turbulent simulation. Okay, good. And well, of course, that's not the first one people have looked into that. And the only paper that I know of that actually looked into numerical viscosity and resistivity is the one by Thomas Rembats and Martin Obergaulinger. And so that's a few years back. I actually talked to Martin Obergaulinger. He was in Dundee and giving a talk on numerical imaging. And so they looked at a different code, and they looked at different Runge-Kutta time steppings, low order, high order Runge-Kutta. And they also looked at different spatial derivatives, stencils, high order and low order. What they found were actually these relatively steep slopes. So they looked also at wave damping. So like on the left, we have sound wave damping with delta x. Okay, using different order of spatial discretization. So you see, it gets very steep for high order discretization, like this black curve over here. And shallow for low order discretization, like fifth order, the green one with the stars. But they also show that there's a difference using different Runge-Kutta methods. You know, Runge-Kutta 3 is more shallow than Runge-Kutta 4. It shows you that the numerical damping, numerical viscosity, numerical resistivity goes down much quicker using high order Runge-Kutta methods, but also high order spatial derivatives. And yeah, that's basically all I had to say. So there's plenty of time for discussions, which is basically what I want to have, you know, a bit of input, a bit of discussion. I mean, we can, in principle, compute numerical viscosity analytically, explicitly, which is something I've been doing with another student. But it seems like we get so many terms, but none of those terms can be safely interpreted as a numerical diffusion, because it never really has, you know, sort of this really nice, simple shape. It always has this one times, you know, some crazy quantities, which I believe, and also talked to some people about it, like Rado in Glasgow. And so I think we all agree that it's very hard to interpret these terms as exactly diffusion. But we also see in the experiments that these numerical terms do behave like diffusion, at least in the context of Raphane wave damping. So that's one thing. And then, of course, we also saw this third order power law, which I still don't know exactly what to make of that, but that's something we can discuss. And that's all I have.
Yeah. Okay. Thanks, Simon, for the this talk. We have like two people who wanted to ask question. Matthias, you can go ahead.
Yeah. Hi, Simon. Thank you for the talk. I have two questions. I would expect that this is not necessarily a Laplacian, what comes in the numerical diffusion. So have you investigated the dependence on the wavelength of the wave? Is there any? Would the lambda star depend on the wavelength? I would expect that. Wouldn't you? You have looked into that, and yeah, you would.
Yes, so, of course, yeah.
It's a hyperdiffusion, right? Which we expect there.
Yeah.
And not, as you said, not completely. So the terms are more involved, but such an experiment should indicate that there is a dependence on the wave number.
Yes, exactly. Yeah. But I haven't done that because some of the simulations take quite a while to get some good data. Yeah. No,
okay.
That's. Yeah.
And the other question, you mentioned that as a side remark, that doing it analytically is possible. It gives very bulky results, and the result is also nonlinear. That surprises me a bit, because if you extend the Taylor series beyond what is in the discretization formula, which is in the code, it would still be a linear term, or all these terms would be linear in the unknown quantity. Why would it be nonlinear?
Yeah, so I think the nonlinearity comes in when you invoke the Runge-Kutta method. So, so if you just have, you know, like say the Euler method.
So okay, yeah, for Euler it would not happen, right?
Then you probably would not happen. But because you have Runge-Kutta, you know, you got this dependence on intermediate steps.
Yeah.
You basically get an analysis in there. And that's actually one of the main difficulties in calculating these things analytically, which are the Runge-Kutta steps.
Okay, that's conceivable, yeah. But in the simplest case, it would still be linear. And you could even investigate that, because the Penzier code does have the Euler method also. If you put IT order to unity, then you would have Euler, and it should not be nonlinear. But you can test that, because you can vary the amplitude of your wave, and you should see that. Have you made this experiment, changing the amplitude? The initial
no, not
amplitude.
the amplitude. No.
The initial amplitude.
No. So I just keep it like 10 to the minus 3 of the background magnetic field, just to keep it small. No, that's a good point.
Okay. Yeah. Thank you.
Yeah. So Axel, you can go ahead.
Yeah, thank you. Yeah, we had discussed this in one of the early pencil code user meetings. It was in 2008, so maybe that was before your time. We did an experiment in that session also. So there was a certain positive diffusion from the scheme itself, which you then can compensate, which we did, by a corresponding negative added diffusion. Is that actually also what you were saying, that you added a negative diffusion for our standard third order time step scheme?
No, I just used the sort of plain.
To get a non-resistive solution, you need to compensate this by a negative diffusion.
You know what? That's something I could test, because so far I only used explicit positive.
So we did,
diffusions.
as I said, we did try that, and it does work. I forget now exactly what the parameters were, but it was something with 10 to the minus 5 in some units. Details have been written down, I believe. I hope, and we need to check that. In any case, the reason for that is coming really from the time stepping scheme. So from the u.grad operator. So the u.grad operator is applied several times, and that therefore indeed you could do get multiple times of u.grad. And in that sense, I think it is for first order and second order schemes, we always have a negative diffusion. For third and fourth order schemes, we always have a negative diffusion. And that I've also seen in earlier textbooks, so it's not a new result. So that is simply what is known. And I also don't think that is what the standard astrophysics community understands as numerical diffusion. When they talk about numerical diffusion, they really think of added schemes to keep this code stable. So for example, when they ask us, what is your numerical diffusion? And I say, yes, it is negative and this and this amount, then they think, oh, but that cannot be true, because it must be, of course, diffusive. And that's why we actually add either explicit diffusion, or some people add shock diffusion, or some people add hyperdiffusion, and some people add a mixture of everything. So therefore, there is a different understanding of what is meant by negative by numerical diffusion. I had a referee who was asking about this, was confused about this, so I explained that in a paragraph in a 2019 paper where we talk about ambipolar diffusion.
Yeah, you're making a good point that this numerical diffusion could in principle also be negative, because there's nothing that tells us that this eta star or whatever quantities we have here is positive. There's nothing that tells us it is positive. In principle, it could be negative.
No, I think the numerical diffusion is what comes out of the diffusion operator, and that is squared, and that means it's always positive, because it's a rounding error. If you square that,
you're talking. Our diffusion error has dispersive errors, so they don't. Or you mean our diffusion? Yeah, sorry, our diffusion operator is also there, but that is there. The error is of 6th order, and I think that's much smaller. There, the modification is much smaller. The main, and that's actually always positive. So the main modification really comes from the time stepping scheme and through the u.grad operator.
Yeah. No, sorry, Axel, I fall in the same pitfall as you. I used the wrong term. So numerical diffusion indeed leads to confusion. And I then ask, do you mean the diffusion from your scheme, or do you mean the diffusion that you add yourself in a proper term? And then it becomes clear then.
Right.
If there are no more questions, let's thank Simon. And